Hello again, folks. Let's make good on that last quiz we saw in the review, right? Let's see what it takes to prove that 0 is a right identity for plus, right? We've already proved that 0 is a left identity. This is a theorem we proved back in day 11, I think. Pretty straightforward that one was. This is going to be a little more tricky. We're going to have to learn not just a new tactic, but a whole new proof method. So in this video, I'm going to go over induction, that new proof method, from Cox's perspective. And then in the next video, I'm going to go over that method on like a virtual whiteboard in a more abstract mathematical way. Okay, so let's see what goes wrong. You might have done this on your own, in which case kudos to you for being a go-getter. If you didn't, that's totally fine. Let's just see what goes wrong. So let's try, right? Intro's end. So you might just say simple, but then, okay, we know nothing happens, right? Because plus is conditioned on its second argument. So let's try the next thing that you might want to do. Let's try it with a destruct. Intro's n. Okay, my case is on n. Okay, the 0 case looks pretty solid, right? What could be bad here? Right? Okay, fine. In the next case, we simplify. The n goes on the outside. But then, how do we make any progress, right? Well, how might we show that these two things are equal? Well, we might want to show that n prime is equal to n prime plus 0. Anybody just have deja vu? Do you just have a deja vu feeling? I have deja vu. Get that? You ever get that? Where it's like, I swear I have seen this before. Where did I see this? Wait a minute. Wait. We wanted to prove, let's take it from the top. We wanted to prove that n equals n plus 0. Right? That's what we set out to prove. And then I said, oh, well, okay. To do that, all I have to do is show that n prime is equal to n prime plus 0. Uh-huh. Okay, well, that sounds a lot like where we started. Maybe we just keep going destructing, right? That's, do some demo work. Okay, this one I feel good about, right? Because, okay, we're good. Maybe this will work, right? Like, we have 1 s of 0, and this is s of 0 plus 0. This is going to be 0. Love it. Okay, cool. We just needed one more destruct, right? Right? So, okay, what do we do here? This is going to be more symbols, but let's stay calm. Okay, s of double prime. We want to be equal to s of, okay, that's good, n double prime plus 0. Okay, great. So all we have to do now is prove that n double prime is equal to n double prime plus 0. We get that deja vu again? Wait. We've been here before. We started with n equals n plus 0, and then we was like, oh, well, I just have to show n prime equals n prime plus 0 for some n prime. Oh, I just have to show n double prime equals n double prime. We're going in circles. This is going to get us nowhere. We could sit here and destruct all day. This is not going to cut it. We need something else. What we need is induction. So induction is the following idea. You want to prove some predicate over natural numbers, like say for all natural numbers n equals n plus 0. Here's the idea. Prove it for 0. That's the ground floor. Then prove that if it holds at n prime, it has to hold at n prime plus 1, at successor of n prime. Okay, and in that idea, you can kind of think of like, well, that's building a staircase, right? If it holds at 0, and we know that if it holds at n prime, it holds at the successor of n prime, then it'll hold at 0 means it holds at the successor of 0, which is 1. Well, if it holds at 1, it means it'll hold at 2. If it holds at 2, it means it'll hold at 3. So, okay, as high as you want to build, you can build up. Another analogy people like is dominoes. Let's say you wanted to prove that 500 equals 500 plus 0. Well, what we have to do is set up 500 dominoes, prove that the first one can be knocked over, that 0 equals 0 plus 0, and then prove that, well, hey, if n prime equals n prime plus 0, then successor of n prime equals successor of n prime plus 0. And that knocks each next domino down until you get to the 500th one. That's what you wanted to see. Okay, that's the intuitive idea. The idea is you take a fact at 0, what's called the base case, and then you prove an inductive case, making an inductive hypothesis, right? If p of n prime holds, then we'll show that the successor holds. And then with these two combined, you can imagine how you might build an argument for any number, right? Like if you have the base case and if you have the inductive case, where assuming the inductive hypothesis you get an appropriate conclusion, then look, it's got to hold for all the numbers. Concretely in Coq, how does that look? So induction is going to take more or less the same syntax as destruct. You can never write an EQN. You shouldn't bother trying. Let's see what we get. So all I've done is change the destruct up top to induction, and I've named one more thing that will appear. This will be the inductive hypothesis here. Let's see what that means concretely. First important lesson to retain for yourself. The base case for destruct and induction is always the same. Okay, so that means our tactic can stay the same. Let's look at what happened to the inductive case. So this looks a lot like the n equals s of n prime case we had back when we got stuck in our destructive loop, our vicious cycle. But we have one more thing. This is the thing that I named. So given some n prime, and assuming that n prime satisfies our identity, we have to show that s of n prime satisfies that identity. This is the inductive game, right? If your property holds for n prime, then go up a level, prove that it holds for s of n prime, and now you can get to any level you want. Using the dominoes metaphor, if you can get to the n primeth domino, show that it knocks over the next one. Show that it knocks over the s of n primeth domino. And then if you can knock over the first domino, the base case, which we've already done here, then you can knock over any domino in any chain of dominoes, however long you want. Okay, this is going to be the thing that gets us out of our destructive loop, right? Why? Well, let's simplify. That says, okay, great, that'll pull the successor out, because that's what plus does, is it pulls successor off of its first thing. But now look, this n prime plus 0, we can use the IH to rewrite from n prime plus 0 into n prime. Check it out. Booyah. Let's see it in prose. For any n equals n plus 0. Prove by induction on n. Okay, first, now we're in the base case. Suppose n equals 0. We must show 0 equals 0 plus 0. Direct from the definition of plus. Okay, next suppose that n equals s of n prime. All right, we're naming our cases. That's good, sort of standard practice for any case analysis, where as our IH, right, this stands for inductive hypothesis. Our IH is n prime equals n prime plus 0. We have to show that same property for s of n prime. Okay, so by the definition of plus, that's just the same as this, which is immediate from the induction hypothesis. Okay, you'll notice we did work up here, right? This rewrite, we just said it is immediate from the induction hypothesis, assuming a human reader will connect this fact and this fact appropriately. All right, we're going to do a lot more informal proof later. I wanted to show this just so you would kind of get a sense of the style. Okay, let's do this one. Minus diag. Here, the idea we're trying to suggest is that of the diagonal. N minus n equals 0. Okay, let's see what happens. So let's go, let n be given. Let's go by induction on n. If we like, let's see this time what happens if we leave off the as pattern, right? Might be good just to see what Coq chooses to do. Okay, so in our base case, we're considering n equals 0. Now, base cases are usually, not always, usually direct and simple, right? Ideally, in a base case, you'll be talking about mostly or entirely concrete values, which means you can just say, hey, Coq, could you figure this one out? Just compute for me. Not going to always be the case, but it's the case here. Okay, let's see what we got here. So one thing that Coq did that I don't love, and part of why I really prefer to write patterns for inductions, is it reused the name of my variable, my original n, for the name of the subpart of n. I find this confusing. You might not, in which case that's okay. I think long term it'll end up being confusing because now really our original n is equal to s of n, which sounds kind of dangerously circular, not the kind of thing I'm into. It's also automatically given us an IH. Now here it says IH and then n rather than n prime because, okay, that's n is the name that it chose. I think it's really nice to name inductive hypotheses with the I or whatever, just to make it really clear where you got it from. Uh, in inductive proofs, there's a sort of Chekhov's gun principle, meaning that if you have an IH, you'd better use at least one of them, right? Depending how many you have. For those not familiar, Chekhov's gun is the idea in set design that if a gun appears on the wall in the first act, then that gun ought to be fired by, say, the third act, right? So your sets should be serving uh, the narrative. Returning to proof, what happens here? Well, if you remember how minus works, if we simple, minus is kind of doing cases on both its arguments. So simple basically gets us where we want to be, and we can simply say apply IHN. Okay. After this, there are tons of exercises. Okay, so there's this exercise, there's sort of all these. And then after this, there's a bunch of optional exercises where I sort of say, this is how you should practice with these. You don't have to do any of these. I think all of these are really good practice. Historically, in this course, we've demanded, I think, a lot more in terms of the number of proofs that you'll do in Coq. I'm trying to reduce that number, but that means by default, you're going to get less practice. Less busy work, but less practice. So it's up to you to decide when it stops being practice and starts being busy work. But I think some of it is going to be a good idea. It's not for credit, though, because I want you to be able to sort of judge these things yourself. That said, even if you do none of them, I really urge you, take a look at the theorems. Applying Chekhov's gun principle, many of these are things that you are going to need again later. So having seen them, okay, having proved them is the best way to remember them, but having seen them will still be really useful for like, okay, these are properties that are really going to be useful for me later, right? This one especially, but things like multi-ASOC and so on. These are important properties of functions we've defined. You want to keep track of them. Okay, that's it for now. The next video I make will be an informal one, going through that sort of stairway up and dominoes knocking over metaphor for how induction works. Okay, talk to y'all soon.